and Bingham fluid, we will do at least one problem of that type, and then you can understand that what can be done and how this analysis can be done, and then you can think for that how the Bingham fluid will work, right? So the Bingham fluid is actually a fluid where it need at least some minimum force to be applied, or shear force, in order to make it flow. So if you have below a particular value, it won't flow, and when you will apply a force beyond that value, actually then it will start flowing and behaving like a Newtonian fluid. So that type of fluids are Bingham fluids. So mostly you can say all type of, not all, but mostly paste type of thing comes in that category, where viscosity varies linearly with respect to the viscosity doesn't vary actually, and the deformation is directly proportional to the applied shear stress. So that happens mainly in case of your toothpaste, something, right? So, so for that is called a Bingham fluid, and and Bingham fluid, because it need a something shear stress to be applied to a some particular value. So those may not be able to flow on a just a one plane or inclined plane or a single plane, because the gravity force which will pull it downward may not be sufficient enough to provide you that much force.
So your voice is not coming.
Whenever the teacher asks question, you say the voice are not coming. Otherwise, everything was fine. Correct? Now, can you hear?
Yes, sir. Your video is still on the same page.
Video is okay, but can you hear whatever I say?
Now it's okay.
So, the Bingham fluids, you cannot make them flow on a single plane or surface. The idea behind that, actually, the body weight or weight of the fluid itself may not be sufficient enough to provide that much driving force, which can go beyond a critical force required to make them flow, actually, right? So therefore, you need a confined space where you can apply sufficient force to make it flow. So at the same time, if it is open to atmosphere or something, then it cannot sustain any type of pressure also, so you cannot apply. So open flow of Bingham fluid is not generally doesn't happen. So you need a confined space, less like a channel or duct or a tube, so so that you can apply the force. So let's see what the problem statement. So problem statement is a fluid of density rho is incompressible laminar flow in a plane narrow slit of length L and width W formed by two flat parallel walls that are distance 2b apart. The gap between two, just like your narrow slit actually. You might have done for that. Have you done for that narrow slit?
I didn't do,
Hello?
sir.
But I asked you people to do it long time back.
Yes, sir.
And any other student? Have you done the question for narrow slit for Newtonian fluid?
Yes, sir. Newtonian weapon.
Yeah, that's what.
That's why I
So
did.
then you have end effects may be neglected, because your this gap between the plate is much more lesser than the width of the plate, and again the width of the plate much more lesser than the length of the plate actually. So the end effects may be neglected. Now, fluid flows under the influence of pressure difference delta P in upward direction. So we have taken upward. Or you can take it by gravity flow if you want to make it downward, or by both. You can apply both. If you are going to upside or downside, you can apply pressure in both the sides, right? So that could be possible. Now, what do we need to find? We have to determine the steady state velocity distribution for a non-Newtonian fluid that is described by Bingham model. Obtain the volumetric flow rate for a Bingham fluid in a slit. Obtain the expression for shear stress profile for a Bingham fluid. Okay. So let's say this is your narrow slit here. So this one is your top surface, and then this is the bottom one. And this is the gap between the plate, which is 2B actually, right? A slit, you can say the width, and slit, you can say height or depth. Width is this actually, the W, and this is the length. So let's say here the choice is yours whether you want to take a coordinate or origin system on the plates or at the center. If you take at the center, you may get some type of the symmetry actually. So half solution will work in the entire segment. Correct? Hello?
Yes, sir.
Sir.
So and then the inclination angle is given theta, and then you have mentioned here at x coordinate is along the length in direction of flow is happening. So pressure is P1 and here. So that way you need to draw your pictures all the time. Now, since the flow is in x direction, so we will directly apply the x momentum balance. So if you will apply the x momentum balance, here I asked you to change this equation just for in terms of shear stress, okay? So if you are taking this, so later on you convert to the shear stress. I hope all of you know these, how these terms are getting cancelled now, right?
Yes, sir.
Yes, sir.
Yes, sir.
So those reasons I still mention everywhere, and you should also keep the habit to mention everywhere. Don't say, okay, it was done long time back. No, every time whenever you are cancelling the term, specify a reason there so that it will become a habit, and you will know that that's why it is happening. So uh, till here the treatment or solution is same, and after that you have got here. So this was you. This is the equation you will get all the time that need to be solved in terms of shear stress. Is rate of shear stress actually you are calculating gradient of shear stress in directly proportional to delta P dash. Correct? This will come in all type of fluid, no matter whether you are taking Newtonian, power law fluid or Bingham fluids. So this equation every time would come. Correct?
Yes, sir.
Now, so you know this that del P upon del X minus rho Gx has been considered here, delta P dash. Now, depending on the type of the fluid we are considering, we can change the expression of shear stress. So in case of Newtonian fluid, you are putting mu du upon dy, and in case of power law, you are putting here eta du upon dy to the power n, right? And for Bingham fluid, you will put tau naught plus minus tau naught plus minus mu du upon dy. So that is for Bingham fluids. So you can solve it for shear stress. Your boundary conditions are this: at y equal to 0 means you have taken the coordinate in the center of the plate, So by equal to 0 means you are at the centers, you are maximum far away from both the sides. So your shear stress can be assumed to be 0, because that is the condition of the maximum thing. At y equal to 0, your shear stress would be 0 actually, because velocity would be the maximum. Okay.
Yes, sir.
So by doing this, if you will solve this, you are getting tau by x equal delta b dash this y, and you are putting here, and then you got your constant equal to 0. So this is your first condition. Now you got tau by x equal to delta b dash y. So this is what will come. Now you have a Bingham fluid. So for Bingham fluid, you can write tau by x equal to tau naught plus mu du upon dy. Now this tau naught which I was talking to you, that is your critical stress minimum threshold volume. So if this applied stress from your side is this one, so if this won't exceed this value, it won't flow. Means the time this value is less than equal to this, your tau by x would be equal to 0. Okay. So there are no the resultant shear stress to make it flow, so therefore it would be 0. Fine. And beyond a particular value, when this magnitude and this would become same, then it will start just 0 only, just 0. And something higher than that, it will make it flow. So this tau naught is called critical stress in that way. So as I mentioned here, that if you are if this value is less than this value, it won't flow, means it will behave just like a solid, and solid you can treat that viscosity should be infinity. Correct or not?
Yes, sir.
Right. So that's here we wrote here. Eta is called apparent viscosity. So it means it is behaving just like a solid. The time this tau by x equal to less than equal to tau naught something. So that is the 0 part. So from here you will get your del u upon del y terms equal to 0 from this particular part, because the difference of these two is 0. So finally this term would come 0 here. Now, what will happen beyond that? So, if it is more than equal to that, you will get this type of the situation, that tau by x equal to minus du upon dy plus minus tau naught. So, where eta is non-Newtonian fluid viscosity and mu naught is the Bingham fluid actually model parameters. So, this is the mu naught. We don't say the viscosity. Now, you can write here when tau by x is positive, so the relationship would become something like that. This tau naught minus del u upon del y. If tau by x is the negative, the relationship would become something like that. So you should say one time it is plus, one time it is minus. So when it's minus, we come from that. Now let's say you have a fluid, as we were talking here. When these two magnitudes would become same, this value would become almost 0, right? Same or less than that. So this value would become 0, right? Tau by x, correct? Hello?
Uh, yes, sir.
Yeah. So after that, as you will move away from this plate, or let's say at the center, so what will have at the center? What would be this value? Del u upon del y. Your velocity would be maximum, correct or not? At the center, because you are maximum far away from the plate. So as your y coordinate would increase, so this value would keep on changing, and there would be a condition that a particular value of y, you are getting this value is less than equal to this till a particular value. It means at y naught or something more than that, this value would be less than equal to this. So your del u upon del y term would be equal to 0. I would come to here only. Uh, What should I say? I hope I might have got somewhere. Uh, this one. So I explained here at these are the boundaries. So you are putting inner plug. So I will tell what inner plug is. So in the center part, your this value actually would be remain constant for a particular value of y till these two magnitude would become same. So therefore, tau by x minus tau naught y would be less than equal to 0, as you will keep on increasing the y till a some particular value of y. So that region is called inner plug flow region because the velocity will not change in that particular part, because both the gate is coming some constant. So in that region, you have considered, let's say, tau by x would be almost will be equal to this tau naught. Is that fine?
Yes, sir.
Now we can write at tau naught be equal to delta p dash y naught, because this is the relationship we already have in the back. Tau by x equal to delta p dash y. So we have just substituted a value of y. Now this would be in this range. So as you will from the center, if you are going something up, so up to some value, same thing downwards. So this would be from minus y naught to plus y naught in that particular range. Fine.
Yes, sir.
And in this particular range, your shear stress would be in this situation actually. Minus tau y naught will be less than equal to this, or tau y x would be less than equal to tau naught, so that you will not have any velocity variation. Now let's see. This is the relationship you have for tau by x, right? Tau by x equal to eta del u upon del y plus tau naught. This is for Bingham model, correct or not?
Yes, sir.
Yes, sir.
Now you can rewrite this eta del u upon del y will be equal to tau by x minus tau naught. Now up to a some particular value that this value will this tau by x will not be equal to this, so it would be less than this something. So it will keep on 0, and the time this will become same. So they will become 0 or less than that. Correct?
Yes, sir.
So final thing, minus is not possible because you should have some finite value. So that's minus thing would also be treated as 0. So you are putting eta del u upon del y should be equal to 0. It cannot be less than 0 something. Now, finally, from here you will get del u upon del y equal to 0. So for u, I just integrate of that, you will get a constant C1. So it means up to some particular value of y, your velocity would remain constant, so that this derivative should remain 0. Fine?
Yes, sir.
And that region is called inner plug flow region. The region, the velocity is not changing. So you will have a flat velocity profile. Now, so this is the condition for inner plug flow part. Same way after that, as I tell in the figure, I can explain here. So if you are here, so if you move this distance up to y naught, this velocity will not change. Same thing, this will not change. After that, what will happen? The time you will reach here, you are going close to the wall. So wall would create the effect on the flow. You go close to a wall is fixed, so your velocity would be 0. Now from here onwards, your velocity would try to change actually, right? Keep on decreasing. So that way is called a outer flow region, right? So that's what the next region is, that outer region. What will happen in the outer region? This is from y naught to b, that you are going to the wall or surface. So now the velocity will keep on decreasing because you are going close to the contact. So after that, if you will apply that, so same thing would be for the lower side. Now your shear stress, the relationship is this: tau by x equal to tau naught minus mu naught del u upon del y. If you are going to plus side, tau by x equal to minus tau naught minus mu del u upon del y. If you are going to minus side, fine.
Yes,
Yes,
sir.
sir.
Now the relationship for your shear stress which we got from momentum balance is tau by x equal to delta p dash y. Correct?
Yes, sir.
Now we can write this. We want to solve for upper side y naught to y less than equal to b. So you got this, that tau naught mu del u upon del y. You can rearrange it. You can write del u upon del y equal to tau naught upon mu naught and delta p dash mu naught y. And you can integrate this. So if you will integrate that, you will get tau naught over mu delta p dash 2 mu naught y square plus c2. Correct?
Yes, sir.
That's fine till here. Now, after that, you have boundary condition. What will the boundary condition? At the wall, you have the no slip conditions. At y equal to b, or you can say plus minus b, your u naught is 0 because you are at the wall. So you will apply at no slip condition. Fine. So applying that, putting this condition here, you can estimate your what is the value for constant C2. Substitute that this is your C2 expression. Fine.
Yes, sir.
After getting C2, substitute here. This would be expression for U naught, tau naught upon mu naught y. Delta p dash 2 mu naught y square delta p dash mu. So you will arrange it. Now this is how your expression for velocity profile in outer region. Inner region we need to calculate. So right, inner region we say at till y naught this velocity is not changing, right? That's what we have calculated. Correct or not? This is what we got earlier, right? Ui equal to C1 for inner plug flow region, right?
Yes, sir.
Yes,
So
sir.
now, because it is the same fluid, it is in contact. So at y equal to y naught, this expression should be valid also, right? Correct or not? Because the velocity profile of same fluid. So this is coming something like that. So at y, if you substitute y equal to y naught, your velocity of inner plug flow region and outer region must be equal, right? This condition must be satisfied. Hello?
Yes.
So you are putting in this expression y equal to y naught here. So if you substitute that, so that condition, now you have one more the relationship here. Tau by x equal to delta p dash y, tau naught equal to delta p dash y naught. This is what we have. Hello?
Yes, sir.
Yes, sir.
So by putting this expression in this velocity expression here, y equal to y naught, and the expression of your tau naught from here, let's see what we'll get. So you have expression for tau naught delta p dash y dash. Substitute here, rearrange it. So if you will rearrange it, and you can get this expression. After that, you will end up with this expression finally, that u naught at y equal to y naught delta p dash b square 2 mu naught 1 minus y naught upon b to the power 2. Why we did that part? Because these are something known parameters. Because tau b or something, these are the fluid properties, but once you will take it, sometime may change it. So you can put a pressure gauge at both the ends, which can be measured much more correctly. So therefore, shear stress expression you convert into the delta P, which are the easily measurable quantity. Correct or not?
Yes, sir.
Hello. So now, as we wrote here at inner flow, that ui at y naught will be equal to u naught y naught, which is equal to your constant c1, nothing but. So you got ui equal to this expression. Now it is valid as far as the y is less than equal to y naught. So okay. Now you will get your u naught expression is this from here. So you got u naught, you have just put y naught here, y naught here. So this is the velocity profile in a flat region. Flat region or your plug flow region. Fine,
Yes, sir.
right? So you got flat region. Now here you can rewrite it in some other the nomenclature also. So this would be your velocity profile will look like. So this is your inner region. In this your velocity is flat. This is your outer region which looks like a half parabola, right? Half parabola part is coming from the square part here because you have here velocity expression is this. So this will give you the parabola part, right?
Yes.
So once you will plot it, you will get this is the velocity. Now let's say you want to make entire velocity profile flat. What can be done? When can it be flat? To make it this flat profile comes in which category? Have you seen in the reactors and all this? Most of the time, you need a turbulent flow, something like that. The reason is that you want a flat profile so that your reactions should proceed forward and you should have uniform concentrations throughout. If you have this type of profile, this fluid will spend more time compared to these one, and these would have different concentration as compared to the inner region, right?
Yes.
Hello. Now,
Yes, sir.
this is one thing. You got the expression. Now, the another way that you can write this way, delta p dash my this you already got. You can drive that this already you have. Then you this expression you already know the for Bingham fluid, right? So I am just saying that this thing can be done in a different way also. This we already talked outer plug flow, the region where this the relationship with hold. So you can rewrite this u naught and this particular part, integrate that, you will get this value. This you got previously also. Now you have at y equal to b or plus minus b, your velocity is the 0. You got the constant there, and then you can integrate it. You will get same thing as we got previously, right? This is the same thing. Hello.
Yes, sir.
Yes, sir.
Now, once we got this velocity, this part we already did, so we will not talk about this further. So this is what you already got. Now we want to calculate flow rate because once you got velocity profile, next thing that how much flow is passing. This is always the concern. So you get flow rate is just v dot dA integrate it over the entire area. Correct or not?
Yes, sir.
So your velocity expression is available with you. So this was something your velocity expression. Now you have the area is nothing but dy into dz. So you can write u dy. Dz is the width of the plate, which is actually w, and this is the symmetry. So minus b to b has been converted to 0 to b. So you got a two factor here. So you got u and dy here, right? Correct?
Yes, sir.
Yes, sir.
Now
Yes,
you can do it integration by parts. So you can take first term, dy let's say second term. So this is the integration by parts. So you have this. After that, you will get this second term. I hope you know the integration by parts.
Yes,
So
sir.
integration
Yes,
of
sir.
the second term, derivative of first term, right? And then this one, right? So that's what you have. So if you'll do that, so let's say what are you getting here? So if you will do it, so you are getting here uy. So this e- the limit is here 0 to b. So one time you can write for b, one time for at 0. Now this term, here you wrote what is your wrote here, y del u upon del y into dy. So let's say here, so you are getting this. Now after that, is it fine here? Uh, that is fine. Integration of second derivative. Is this correct, no? Or something wrong? It's correct, I think. So now you have here. So what you have in this range? Can you see here? At y equal to v, what would be your velocity? Hello? What?
Zero, sir.
Yeah, 0, because it is no slip condition. So at y equal to b, your uv is 0. That's what you have here. At y equal to 0, your velocity is maximum. So what is the benefit of that? That this product is also getting 0. This product is also getting 0. Fine. So
Yes, sir.
you are leaving only with this term. So let's see what you have here. So y del u upon del y into dy. Okay.
Yes, sir.
Now we can integrate it there. So you have this relation tau by x equal to delta p dash y. So let's say at the wall at y equal to b, you can write tau bx because y you are calculating at b actually. So you can write delta p dash. And therefore, corresponding y is b. So you can find the ratio of these two. So ratio of these two would be tau by x upon tau bx would be equal to y upon b because the ratio of these two. So delta p dash will cancel. So you will get the relationship from here. Del tau. So you got tau by x equal to y upon b tau b. You can differentiate it with respect to y. So you are getting del tau by x upon del y equal to tau b upon b. Is that fine? Differentiation of this because y will get cancelled only. So from here you will get what is your del y. So del y equal to b upon tau b del tau by x. Hello.
Yes, sir.
Now this is your equation number 8. Let's say this is your equation number 5. 5 may is you need this del u upon del y, right, and into dy. So you got an expression for dy. What is your dy here? So you are substituting here. So dy at the place of del y, you are putting b upon tau b del tau by x. This is this term. This you already have del u upon del y in your expression number 5. This is an expression of y. Y would come from here. So y would be tau by x upon delta p dash, right?
Yes, sir.
Yes, sir.
So that is here tau by x upon delta p dash. So everything you have converted in terms of shear stress now, right? But you have something del u upon del y also. So let's see if you will rearrange it, what are you getting? Now you have one term delta p dash. So at the delta p dash you wrote here tau b upon b. That is from this expression delta p dash you are just putting this is tau b divided by b. So that is coming at this particular place for delta p dash. Hello.
Yes, sir.
Yes, sir.
Now you can rearrange this, so you are ending up with this expression minus 2w b square upon tau b square 0 to b tau by x del u upon del y del tau by x. Now you have this expression, right? Tau by x equal to tau naught plus mu del u upon del y, right? You have this,
Yes,
correct?
sir.
Now you can do integration by parts of this again. So at this place, at the place of tau by x, you are substituting this expression here. So you have here tau by x here, this at the place of del u upon del y, this one that you wrote tau by x minus tau naught upon mu, and this you already have. So this term is as it is. This you are doing now here for from here, and then you got this. Now let's see further. So you have this. Now you can do it further integration by parts again from this one. First you do this particular part here. So let's see what you have here. So first you are getting this tau by x upon del u upon del y d tau by x. So you are actually differentiating this entire the limit of 0 to tau b, because 0 to tau b from center till your surface, correct? Hello?
Yes, sir.
In between of that, you will have somewhere tau naught also, correct or not? So you have this entire the limit of shear stress, you are divided into two parts, 0 to tau naught and then tau naught to tau b. Fine.
Yes,
Yes,
sir.
sir.
Now this expression you already have from here, tau by, only thing you have divided is 0 to tau naught and tau naught to tau b. So this you will get. Now what will happen in this region? 0 to tau naught, this del u upon del y term is 0 as we got previously, because this is your inner plug flow region, correct or not? In this your velocity is constant, so therefore your derivative is 0. So this term is getting cancelled. So you are living with this term only. Okay? Hello?
Yes, sir.
Now this need to be integrated. So you have this. Now you know the expression of del u upon del y in terms of this. So you tau 1 and x minus tau naught upon mu into dyx. Now you have everything in terms of shear stress. So that can be integrated easily. So just integrate that, you will get this expression. After that, substitute the limit tau naught to tau b. You will get this expression here. One time with tau b, another tau with tau naught. So if you will do that, so now you take the common here. So you are ending up with this equation tau naught cube upon 3 something. Then again you take common from here, so you will end up with this is 2 wb square upon mu naught tau b upon 3 minus tau naught by 2 1 by 6 tau naught cube upon tau b cube. So this again you can take further, you can rewrite it in terms of tau b. So let's say what you have, because tau is b, generally we need to calculate somehow in terms of measurable quantity. So tau b is this delta p dash b, because we want to have all expression in terms of measurable quantity, easily measurable. So this expression again tau b is being converted to in terms of delta p dash. So if you write that, so first expression of flow rate is coming in terms of this one. So you are getting here minus 2b b cube w upon mu naught delta p dash 1 by 3 1 by 2 tau naught upon tau b plus tau naught upon tau b cube. So this is the expression expression you have. So you can change this expression tau b also in terms of delta p dash b. Then it will become in terms of measurable quantity. But this is also a standard form. People want to show that. So this is the expression for your volumetric flow rate. Suppose you have the Newtonian fluid. Newtonian fluid, does it have tau naught? Hello?
Yes, sir.
No, sir.
Yes, no. Newtonian fluid doesn't have tau naught. So tau naught is zero. So this term would get cancelled. This will get cancelled. Finally, you are ending up this equation, which is same, which you have already derived for the previous one, right? Newtonian fluid in the narrow slit. You got this expression. So it means whatever you did here is correct. Okay.
Yes, sir.
So that way, it completes the flow of Bingham fluid in a plain narrow slit, and it can be only in a confined only. So you don't have to do for upper plate, bottom plates, and all this. In delta p dash, we have considered everything. So delta p dash is del p upon del x minus rho gx. So you can change delta p dash by this expression depending on your orientation, what is the applied thing. So this is valid for all type of configuration, right? Okay.
Yes, sir.
Yes, sir.
So try to understand it. You will have video of that. Try to solve it by your hand. And if you have any doubt, any confusion in any step somewhere, so that we will discuss in next class. Okay.
Okay, sir.
Sir.